Imagine a really severe fracture, or maybe after surgery, like removing a tumor, you're left with this big gap in a bone. It's a tough problem. For years, orthopedic surgeons have been trying to find ways to fix these critical defects in ways that are really custom fit. But what if you could actually print the perfect replacement part, tailored exactly to your body right there during the surgery? So that's what we're really digging into today, this groundbreaking idea. A portable in situ 3D printing device. It could totally change how we heal major bone defects. And it's not just patching things up. We're talking about engineering living tissue with amazing precision. Our deep dive today is based on insights from a really brilliant review by Dr. Reza Lankarani. He's a general surgeon, founder of the Surgical Pioneering newsletter and podcast series, and also an editorial board member of the Genesis Journal of Surgery and Medicine. He's helping us understand a key article by Gian and colleagues published this year in the journal Device. So our mission basically is to figure out how this, bone glue gun actually works. Why is it such a game changer? And what could it mean for personalized medicine? Get ready for some ha-ha moments.
Yeah, it's a really fascinating problem they tackled because, even with all the advances we've made in medicine, treating these really significant bone defects is still.
Oh, hey there, what's up?
This is Dr. Reza Lankarani speaking. I just wanted to mention that why I was interested in this review of mine. First of all, because of my father, who is an orthopedic surgeon, and I was always wondering from long time ago what kind of composition they used to fix the bones. And when I read this article, I thought it would be a good subject to discuss, and especially from you guys, because you are diving into every detail. So I'm wondering how you going to describe all of these things. And
Dr. Lanker.
Uh-huh.
And sorry to interrupt you. I don't want to interrupt you anymore. I just wanted to say thank you and have.
Dr. Lankarani, please, no apologies at all.
We absolutely love having you here.
Your insights are incredibly valuable.
And knowing your personal connection through your father, that just makes this even more special.
It's wonderful that this topic resonated so much with you.
And really, it highlights why this research is so crucial.
That personal connection, it really grounds the science, doesn't it?
It definitely helps us understand the why behind the research.
And it makes us even more excited to unpack all the details for you.
So please chime in anytime.
We welcome all your thoughts and questions.
It truly enriches the conversation for everyone.
So we were just getting into the existing challenges.
Treating these really significant bone defects is still, it's one of the big challenges in surgery.
Imagine a bone loss from, bad accidents or severe infections.
Maybe even after removing a tumor, leaving a critical gap.
The usual ways, using the patient's own bone called an autograft.
Or using donated bone allografts, they often run into problems.
Limited supply for one, especially for larger defects.
And there are risks, like pain where they took the bone from for autografts.
Or other complications for the patient.
And even the artificial implants we have.
They can give some stability, sure.
But they often struggle because bone defects, they're not neat shapes, are they?
They're complex, irregular, like you mentioned with your father's work.
So if the implant doesn't fit perfectly, it doesn't integrate well.
And that leads to problems down the road.
Right. So it's like the body needs this incredibly specific custom part.
But our current tools are more like off-the-shelf solutions.
And they often just don't quite fit the bill.
It sounds like the traditional methods are kind of fighting against how complex the body actually is.
Exactly.
So what were those fundamental problems that current methods still struggle with?
So take autografts, the patient's own bone.
Biologically, that's the gold standard. No rejection issues.
But getting enough bone for a really large defect.
Often just not possible.
Plus, you're creating a second wound site, which can be painful, cause complications. Allografts, the donated bone, help with the supply issue. Yeah.
But there are still risks, screening, potential disease transmission, though rare.
And ethical points, too.
And then the artificial implants, polymers, metals.
They're great for immediate mechanical support.
But like you said, they're usually rigid, fixed shapes.
Trying to jam a standard shape into a really unique, irregular hole in the bone.
Well, it often doesn't work that well.
The bone doesn't properly grow onto or into the implant. That's osseointegration.
And that can mean it gets loose or fails completely over time.
This is exactly why Dr. Lankarani's interest in the composition is so relevant.
Because it's about finding something that not only fits, but also works with the body.
And that's what we're going to dive into next.
We're so glad you're here for the journey, Dr. Lankarani.
Thank you again for joining us.
We'll be right back after this short break.
So, take autographs, the patient's own bone. Biologically, that's the gold standard, no rejection issues.
Yeah.
But getting enough bone for really large defect, often just not possible. Plus, you're creating a second wound site, which can be painful, cause complications. Allografts, the donated bone, help with the supply issue, yeah, but there are still risks, screening, potential disease transmission, though rare, and ethical points too. And then the artificial implants, polymers, metals. They're great for immediate mechanical support. But like you said, they're usually rigid, fixed shapes. Trying to jam a standard shape into a really unique, irregular hole in the bone, well, it often doesn't work that well. The bone doesn't properly grow onto or into the implant that's osteointegration. And that can mean it gets loose or fails completely over time.
That makes total sense. And we've seen amazing things with 3D printing, right? Like custom prosthetics or surgical guides made outside the body. So you think, why haven't we just used 3D printing for this bone defect problem already? What stopped us from bringing that custom approach right into the OR?
That's a really important question. People have seen the potential of 3D printing for custom implants for a while now, but the process itself is, well, it's cumbersome. Really cumbersome. Usually you need high-res scans of the defect, then lots of complex data processing, designing the implant on a computer. Then you send it off to be printed on these big, expensive industrial 3D printers somewhere else entirely.
Offsite.
Exactly. And then after it's printed, there's often a lot of post-processing, cleaning it, sterilizing it, making sure it's strong enough, all before it even gets to the surgeon. That whole workflow just takes too long, costs a lot, and isn't practical for the immediate needs of surgery. It's been a major roadblock.
Got it. So the big goal was clear. Find a way to get that amazing customization power of 3D printing right there at the point of care, something that could adapt instantly to the patient's specific injury. And that's exactly what this research by Jan and colleagues does. It's a whole new way of thinking.
Yeah.
Okay, so here's where it gets really, really interesting. The core concept is this portable in situ 3D printing device. Picture it almost like a specialized sterile pen, maybe a bone-building pen that the surgeon actually holds. And it extrudes these biomaterials directly into the defect. So what are they actually using? What materials make this possible?
Yeah, the materials are absolutely key. The main one is something called polycaprolactone, or PCL. PCL is a great choice. It's very biocompatible. The body accepts it well, and it's biodegradable. So it's designed to break down safely over time as new bone grows in. And here's the critical part. PCL has a pretty low melting point, only around 60 degrees Celsius.
Oh.
That's vital. It means they can extrude it without needing harsh chemical solvents, which could damage tissue. And it keeps the heat exposure to the surrounding bone really low during printing. Then mixed in with a PCL, they use hydroxyapatite, or HA.
HA, like what's in our actual bones?
Exactly. It's a natural mineral that makes up a big chunk of our bone structure, gives it hardness. By putting HA into the mix, they boost the implant's mechanical strength. And really importantly, it enhances osteoconductivity.
Osteoconductivity, meaning it helps new bone grow.
Precisely. It actively guides and encourages new bone cells to form on and around the scaffold.
Wow. The genius seems to be in how simple yet adaptable the device is. It's basically a hot melt extrusion method, like a really sophisticated glue gun, right?
Right.
This design means the surgeon can literally print and sculpt the material right onto the defect. No more pre-making things, no post-processing. And you mentioned something fascinating by changing the mix, like the amount of HA or the type of PCL. They could actually tune the properties. How does that tunability help a patient?
Oh, that tunability is absolutely central to the whole idea of personalized medicine here. Think about it. Maybe a patient needs an implant in their wrist bone that doesn't take a lot of load versus, say, an implant in the femur, the thigh bone, which carries a lot of weight.
Right, very different demands.
Exactly. So with this tech, the surgeon could potentially choose a material stick with more HA and a specific PCL type to make a stronger scaffold for the femur. But for the wrist, they might choose a different mix, maybe one that degrades a bit faster or has different biological cues. It lets them tailor the implant's stiffness, how fast it breaks down, how well it encourages bone growth, all tailored to that patient, that bone, that specific defect shape. It's a huge leap from the one-size-fits-most approach. It's truly custom.
So it's not just filling a space, it's creating this dynamic structure that actually works with the body's healing. But, okay, the real test isn't just filling the hole, is it? It's making sure that the new stuff actually becomes functional, living bone, and that it lasts long enough for that to happen. So how did they make sure the implant had the right strength and, degraded at the right speed?
Well, it starts with how they make the material sticks themselves. They mix the PCL and HA together really thoroughly at 180 degrees Celsius, crucially. No organic solvents involved. And then they solidify this mix into these thin sticks.
Okay.
Those sticks then get fed into the printing device. They played around with the HA levels and found that up to about 25% HA by weight worked best. Any higher, and the material got too brittle, could even clog the printer nozzle.
Ah, okay.
And to be sure it was all consistent, they used some pretty advanced techniques like spectroscopy and special staining methods. These tests confirmed the HA was perfectly mixed in, spread evenly through the PCL. That's vital for it to behave predictably.
And the strength, could they really adjust the strength for different bones?
They definitely showed they could. Things like compression strength and elastic modulus, basically, how stiff it is, both went up significantly when they used higher molecular weight PCL or added more HA. For instance, the mix with the highest PCL weight and 25% HA, which they called 50H, was the strongest.
So a surgeon could literally pick a formulation for a heavy-duty job, like a leg bone.
That's the idea, yes.
Yeah.
They also tested how well the printed material stuck to actual bone using cow femurs. Adhesion got better with higher PCL weight, probably because the longer polymer chains get more tangled. Interestingly, though, adding more HA slightly reduced the adhesion.
Oh, really? Why?
The thinking is maybe the HA particles kind of get in the way of the PCL interacting directly with the bone surface. But even with that slight decrease, the adhesion strength they measured was still well within the range considered clinically okay for bone adhesives.
That's fascinating. Okay, so it's strong enough it sticks, but then it needs to disappear gracefully, right? To make way for real bone. You said PCL is biodegradable. How did the HA affect that breakdown process?
Yeah, that's another critical piece of the puzzle. The scaffold needs to hold strong while the body heals, but then it needs to slowly dissolve as new bone takes over. PCL itself breaks down over months, maybe even years. But what they found, interestingly, was that adding HA actually slowed down the degradation.
It slowed it down.
Yeah, the pure PCL broke down faster than the mixes containing HA. And this controlled, slower degradation is actually a good thing. It means the implant provides that mechanical support for longer during that really crucial initial healing phase. It gives the patient's own bone cells the time they need to rebuild without leaving a permanent foreign object behind. It's like a carefully choreographed dance between support and replacement.
Okay, so they nailed the mechanics, strength, degradation. But let's step back. A huge risk in any surgery is infection. Can this bone-building pen also fight off bacteria? That would be amazing. This is where it gets really clever. The researchers actually figured out how to incorporate antibiotics into the composite material. Not just one, but two. Vancomycin, which targets gram-positive bacteria, and gentamicin for gram-negative ones. And it's designed for sustained release, so it creates this little protective zone right where it's needed most. This is huge, because infections after open fractures are a big problem, can happen in up to a third of patients.
Wow, sustained release antibiotics too.
Exactly. And they found both drugs were released steadily over several weeks. Gentamicin came out a bit faster, probably because it's a smaller molecule. And get this, adding the HA actually seemed to increase the drug release. Maybe because HA is more water-loving.
Interesting.
To prove it worked, they did standard lab tests, disc diffusion assays, and they saw clear zones where bacteria like E. coli and S. aureus couldn't grow. So yeah, it definitely packed an antibacterial punch.
That's incredibly smart. But beyond antibiotics, what about the heat? You mentioned it melts at 60 degrees, but even that sounds warm to be putting directly onto tissue. How did they manage the heat to keep things safe?
Right. You can't just use a hot device inside the body without thinking about thermal damage. That's another area where the engineering is quite elegant. They put a special kind of chip in the device, a positive temperature coefficient or PTC type chip. You could think of it like a very precise self-regulating thermostat.
Okay.
So they made a custom version with an 80 degrees Celsius PTC component. And this managed to lower the temperature right at the tip where the material comes out to around 55 degrees Celsius.
Cool.
That's way down from over 120 degrees in devices without the control. And importantly, it also meant the extruded material cooled down to body temperature much faster in about 40 seconds. So they effectively designed out the risk of thermal injury.
Very clever.
And then the final piece, really biocompatibility and actually promoting bone growth. An implant can't just be a passive space filler. It needs to be friendly to cells and actively encourage healing, right? Definitely. Does it just sit there, or does it actually help the body rebuild?
The results there were really positive too. They did lab tests with pre-osteoblasts, those are early stage bone cells, and also with human bone marrow stem cells, the HPMSCs we mentioned. They found the materials weren't toxic at all, which confirms they're biocompatible. And the cells attached well and grew happily on all the PCL-HA scaffolds. But even better, adding the HA significantly boosted the ability of those stem cells to turn into actual bone cells. They saw more calcium being deposited, higher levels of key bone-building markers. So it tells us the implant isn't passive. It's actively signaling and stimulating new bone formation. It's osteoconductive.
Okay, lab results look great. But the real proof is always in a living system, isn't it? So how did this whole approach work when they moved from the benchtop to an actual animal model?
Exactly. They moved to an in vivo study using rabbits. They created critical size defects in the rabbit's femur's thigh bones to mimic a challenging clinical situation. They used that 50H formulation, the one they found had the best mix of strength and biological activity. But before they even did the surgery, they used something called finite element analysis, FEA. It's basically a powerful computer simulation.
Ah, like virtual stress testing.
Precisely. They used FEA to predict how the scaffold would hold up under normal physiological loads, like walking. The simulation predicted it would last for over 160,000 loading cycles without failing. That showed it should be really robust and stable, even in a weight-bearing bone, which is obviously critical.
That's amazing foresight, stress testing it virtually first. What happened in the actual rabbits after 12 weeks? The results sounded really promising.
They were very encouraging, yes. When they looked at the tissue samples, under the microscope, that's histology, they saw really robust new bone formation, lots of healthy collagen-rich bone growing around the PCL-HA scaffolds. And it performed significantly better than the standard commercial bone cements they used as controls. Wow. Then they use micro-CT scanning, which gives these super detailed 3D images of the bone structure that confirm more new bone formation, increased bone volume, more surface area, and importantly, the regenerated bones seem mechanically better too. The measurements suggested a more natural, stronger internal architecture compared to controls. And crucially, from a safety perspective, they saw no signs of tissue death, no weird inflammation, no signs of the implant pulling away from the existing bone. Everything looked good.
That really does sound like a success, not just filling a hole, but actually regenerating real functional bone tissue. When you look at the bigger picture, this portable in situ printing feels like more than just one new tool, doesn't it? It seems like a whole platform technology.
I think that's exactly right. The ability to, custom tune the mechanics, control the degradation, dial in the osteoconductivity, all based on the patient's specific needs, the defect location, the shape, how long it needs to heal. That is a massive leap forward. It really moves us towards truly patient-specific bone repair, giving the body exactly what it needs, precisely when and where it needs it. It optimizes the whole process for better long-term function and ultimately better patient outcomes.
It's genuinely exciting. But of course, with any new technology this groundbreaking, there are always next steps, right? What are the researchers focusing on now? What's the path ahead?
Yeah, the authors themselves highlighted a few areas for future work. One is continuing to improve the mechanical properties, making it even stronger for long-term use, especially in those really high-stress bones. Another is optimizing the printing process itself, maybe different nozzle shapes for more complex structures, or designing specific porous patterns within the scaffold to better mimic natural bone. And then, of course, there's the path to getting it into actual human use. That involves scaling up manufacturing, navigating the whole regulatory approval process, which is complex, and then conducting larger clinical trials in people. So there's still work to do, definitely. But the foundation they've laid is incredibly strong. The potential is undeniable.
What an absolutely fascinating deep dive. We've really unpacked how this portable in situ 3D printing device using these smart PCLHA materials offers this incredibly personalized and multi-talented solution for major bone defects. It's not just about structure. It's about encouraging new bone, fighting infection, and doing it right there on the spot.
Yeah, the ability to tailor everything, the mechanics, the breakdown, even adding drugs like antibiotics all at the same time for that specific patient. That really represents a significant step forward in orthopedic care. It holds tremendous promise for improving how patients heal, how quickly they recover, and their long-term function. It's really pushing the boundaries of regenerative medicine.
So think about what this means for you listening. Beyond fixing bones, this whole idea of in situ personalized manufacturing, it opens up so many possibilities across medicine. Could we imagine adapting this tech for other tissues, maybe printing cartilage repairs directly in a joint, or even more complex soft tissues? What other huge medical challenges could this kind of printing press for the body help us tackle down the line? Something to think about. This deep dive was based on the profound review and insights from Dr. Reza Lankarani, an editorial board member of the Genesis Journal of Surgery and Medicine. To access additional details and to explore more pioneering surgical innovations, please do check out the Surgical Pioneering podcast series application. It's available at https.surgicalpioneer.codx.me. We definitely encourage you to explore and continue your own deep dive.